Hi, today we'll be learning about integration using trigonometric substitution. Before we learn about trig substitutions, we should review. Trig and derivatives. Integrals in trig. Trig identities. Fantastic! Now we know trig. So now let's review something we call use substitution. How would you solve this problem? You used use substitution, right? Well, hopefully this is how you did it. So first you should substitute 9 minus x squared for u, and then take the derivative, so du equals negative 2x dx. And then you have negative 1/2 du equals x dx. Then you plug that back into the equation, and you get negative 1/2 over the square root of u du. And then you can simplify that all the way to over here. So it simplifies out to negative 1/2 of the integral of u to the negative 1/2 du. So then you simplify that out using your knowledge of integrals, and you get negative square root of u. And then you plug back in 9 minus x squared equals u, and you get negative square root of 9 minus x squared. Wow, thanks, use substitution. But how would you solve a problem like this? Go ahead and try, but you can't use substitution. What you should do is use trig substitution, using these formulas. So what you see here is a pattern of square roots and variables that are squared. So if you see that in a problem and you think you can't integrate, that probably means you should use trig substitution. So let's go back to that problem. So what you should have noticed the first time when you used use substitution was that the derivative of this under the radicand did not equal this, and that was a problem. So when you substitute in trig functions, you'll get something that's solvable. Let's see. So if you remember this chart, you'll see that the square root of a squared minus x squared is in this equation, and it will equal x equals a sine theta. So using the trig substitution and this formula that we just discovered, we can see that a equals 3 in this case, so that x equals 3 sine theta. And then we take the derivative like we would when we use substitution, and dx would equal 3 cos theta d theta. So you plug back in 3 sine theta for x and 3 cos theta d theta for dx, and you get this equation here. And you can see if you do more algebra that 3 squared will be 9, and then sine squared will be sine squared, etc. And you'll get that equation. You'll get this equation right here. So then you can move some of the constants we had in front of sine and cosine to in front of the integral. And you can simplify the square root of 9 minus 9 sine squared to 3 times the square root of 1 minus sine theta using the identities. Remember these? Well, you can use the first equation to get cos squared equals 1 minus sine squared. So now that you've used that identity, you can get the square root of cos squared theta over sine squared theta. And since the 3 that was before the radicand in the previous equation can be moved to in front of this integral, we get 9 over 9, which cancels out to 1. So if you put that all together and you do the square root of cos squared theta, you'll get the integral of cos theta times cos theta over sine squared theta d theta. And since we know that cos squared theta over sine squared theta is cotangent squared theta, we get the integral of cotangent squared theta d theta. And since we don't know the integral of cotangent squared theta d theta, we should use identities. And if we go back to this again, we can see that cotan squared can be cosecant squared minus 1. So using that identity, we get the integral of cosecant squared theta minus 1 d theta. And using your knowledge of integrals, you get negative cotangent theta minus theta plus c. Yay, that's our answer, right? Nope. So we've done all this math and we come to the conclusion that the answer should look a little bit like this. Unfortunately, the equation we started with is in terms of x. So we go all the way back to x. And we've already established that x equals 3 sine theta. So if we're trying to get x back into the equation, we should substitute sine theta for x over 3. So now that we have our x in terms of sine theta, we have to get it in terms of cotangent theta. So we use this crafty triangle. And so if we remember our SOHCAHTOA, we know that sine is opposite over hypotenuse. And we find the third side to be the square root of 9 minus x squared. So we know that cotangent theta is 1 over tan theta. And using the rules that tan is opposite over adjacent, cotangent must be adjacent over opposite. So we get that cotangent equals the square root of 9 minus x squared over x. So if we plug back in the square root of 9 minus x squared over x for cotangent theta, we get negative the square root of 9 minus x squared over x minus x plus c. And that is our answer. Yay, that was so exciting! Bet you want to do another one. So find the answer to this one. So here again we have a square root with an x squared underneath the radicand. That usually leads to the use of trig substitution. So think back to the formula sheet we had before. Which one would we use? So if you look back on this chart, you can see the first formula can be used to solve our equation. So just like before, we're going to find the derivative of x, and that would be the square root of 3 over the square root of 2 cosine theta d theta. And then you plug that all back into your previous equation, and you get the integral of 1 over the square root of 3 minus 2 times the square root of 3 over the square root of 2 sine theta squared times the square root of 3 over the square root of 2 cosine theta d theta. And if you do some canceling out and factoring, you can see that when you square the square root of 3 and the square root of 2, that just becomes 3 over 2. And then you can cancel out the 2. And then you can factor out the 3 in the bottom, so you get the square root of 3 times 1 minus sine squared theta. And then you use the identities again. So once again, you can substitute cosine squared theta for 1 minus sine squared theta. Once you've plugged in cosine squared theta for 1 minus sine squared theta, you get the square root of 3 over the square root of 2 times cosine theta d theta over the square root of 3 times cosine squared theta. And then you do some more canceling out, and so since you can separate the square root of 3 from the square root of cosine squared theta, you can ultimately get the square root of 3 times cosine theta on the bottom. And there is a square root of 3 times cosine theta on both the numerator and the denominator. You can just cancel those out to get a much simpler version, which is the indefinite integral of 1 over the square root of 2 d theta. And then using your knowledge of integrals, you can get 1 over the square root of 2 theta plus c. But once again, that's not the answer. You have to get it back into terms of x. Oh no, I hate x! But we have to go back to x. So we remember that x equals the square root of 3 over the square root of 2 times sine theta. And when we solve for theta, it is arc sine square root of 2 over square root of 3 times x. And when we plug that back in, we get this. We get 1 over the square root of 2 arc sine square root of 2 over 3x plus c. See, isn't using trig substitution fun? It only took me 1 whole page to do a problem. Let's do another. And so the pattern continues, and we have a square root of an equation that contains x squared. So figure out which formula we would use for this one. Go back to the sheet, and we see that the second formula works out for this equation. Right there. So this time we use the square root of b squared times x squared minus a squared, where a equals 2 and b equals 5, so that x equals 2 over 5 secant theta. Then we take the derivative of x, and we get dx equals 2 over 5 times secant theta times tan theta d theta. Now that we know what x and dx are, we can go back and plug in. So we get the indefinite integral of the square root of 25 times 2 over 5 times secant theta squared minus 4 over 2 over 5 secant theta times 2 over 5 times secant theta times tan theta times d theta. We do a lot of canceling out. So we cancel out 25 with the 2 over 5 squared, so that would be the 25 cancels out with that 25. And then we cancel out the 2 over 5, which is in the denominator, and the 2 over 5, which is in the numerator. And so we get to this step where we can factor out the 4, because now we have 4 times secant squared theta minus 4. Now we get the square root of 4 times secant squared theta minus 1, and we can use an identity. Okay, so now we can substitute secant squared theta minus 1 for tan squared theta because of the second identity. We can cancel out the secant theta in the numerator with the secant theta in the denominator. So now that's gone. And we've also substituted tan squared theta for secant squared theta minus 1. And we moved the 4 from inside the radical to outside the radical, and now it's a 2. And so we can move on to the integral of 2 times the square root of tan squared theta times tan squared theta d theta. So you move the 2 from inside the integral to outside the integral, and you take the square root of tan squared theta, and that's just tan, and you multiply that by tan, and so we get 2 times the integral of tan squared theta d theta. And then we're going to go back to our identities and substitute secant squared theta minus 1 back for tan squared theta. And that makes this much more integrable, and we get 2 times tan theta minus theta plus c. But we're not done. So like in the previous examples, we have to move back to terms of x. So x equals 2 over 5 secant theta. And if we're going to use the SOHCAHTOA theory, we have to get secant theta isolated. So we have secant theta equals 5x over 2. And we get this triangle using Pythag. We all know Pythag, don't have to explain that. So we use this triangle to figure out how to get tangent theta into terms of x. So we know from SOHCAHTOA that tangent is opposite over adjacent. So when we have opposite is the square root of 25x squared minus 4, and adjacent is 2. So we get tangent theta is just that. It's the square root of 25x squared minus 4 over 2. And so to fully convert this answer into terms of x, we have to figure out what theta is. And so we know that x equals 2 over 5 secant theta. So theta must equal arcsecant 5x over 2. And then we plug that all back in, but we realize we can cancel out some more things, so we can cancel out the 2 in the numerator and the 2 in the denominator. And our ultimate answer is the square root of 25 squared minus 4 minus 2 arcsecant 5x over 2 plus c. Hopefully you understand the concept by now. Here are some more equations you can do on your own to test your knowledge. Good luck! And here's another. And here's another. And another. And another. So now that you've done all these equations, you need the answers. Here's the answer key. So my video has come to an end, and I hope you learned a little something about integration using trig substitution. Thanks for watching.
I've never taken calculus before, but now it makes so much sense. Thanks, Serena.